I've come down to Hasco Foundry to have a look at how we pour a cylinder head and block, show you through the whole process from beginning to end, and we are going to learn how the future of the RB will be manufactured. All right, I'm standing here with Adam from Hasco Foundries, and we do all of our casting here in Australia. We're going to hear a little bit about the foundry, and then we're going to talk about our RB blocks and heads that all get done here. Thank you, Adam, and I'll let you tell us a little bit about why you do this insane, hot, sweltering business.
We're Hasco Foundry. We're a small family business. We've been operating since the mid-80s. It started out as a small backyard operation before we migrated to this shed. We do ferrous casting and non-ferrous casting, so we can do both cast iron and aluminium castings for the performance auto industry, amongst various other industries that we serve as well.
I've seen some brasses and...
brasses and bronzes. We do rail, aero, transport, performance auto, mining, fuel nozzles.
Fuel nozzles, yeah.
Being a low volume jobbing foundry, we do pretty much whatever people bring in, we'll have a crack at. Because all the volume stuff's gone overseas, so you've got to do the small, niche, high quality stuff.
I've seen some 202 cylinder heads.
Yes, yep, we do a 202 red motor cylinder head. The V12 LS we do as well.
And then we thought we'd ruin your life with an RB.
No, we love it. What are you talking about?
So what we're going to do now is go through the whole process step by step, and I guess we start at the beginning.
Yep, we'll start looking at 3D printed cores and go from there.
So now after we've got our 3D printed core, this is all pre-production type stuff. We're not going to talk about full production stuff because we've got a lot of IP, and we're also not going to show you what our core looks like because it's very tricky, technical, and we don't want to give away secrets. But we do have the 202 one that we've just been able to video. Gives you an idea of what the middle looks like. Basically, there's all these sections that separate all the oil galleries, water gallery, levels, combustion chamber and ports. So all of that has to come together into an intricate layered core. Once we have that core, it goes over to our continuous mixer. Yep. Tell us how that works.
So the continuous mixer is basically the way that foundry castings have always been made since we had the introduction of phenolic resins. You've got a pattern, your pattern is a frame, so you fill the frame with sand from the mixing machine. That sand then sets and becomes half of your mould. You do that for the other half of the mould, so most of the moulds that we make are going to be two-part moulds with the bottom and the top. We call the bottom the drag and the top the cope. And then if you've got intricate geometry inside the casting, like you do with a block or a cylinder head where you've got jackets, oil galleries and whatnot, ports, the best process to do that is to 3D print the cores as we've talked about. Then you drop the core into the bottom half of the mould and then close it on top. So once we've got the two halves of the mould together with the cores inside, it's ready for pouring. So we move it down the line to the furnace area, melt and prepare the metal, and then pour the castings.
Let's have a look, can't wait.
So behind me here, we've got the patterns that we've filled up with sand from the continuous mixer. The patterns form the bottom half and the top half of the mould when they're filled with sand. So once it's filled, it's got a certain amount of time for the sand to set. In our case, we've got it set to about 10-15 minutes. Then you roll the mould over, strip the pattern off. Pattern goes back to the continuous mixer to get filled again for the next one. And then the moulds get assembled further down the line before we pour them.
Explain to me the filling tubes. At the top you can see those ceramic.
So we've got an insulating sleeve there, and the idea behind the insulating sleeve is that as you've got a molten casting inside the mould solidifying, it's expanded in the molten state, and as the metal solidifies it contracts, and as it's contracting we need a hot reservoir of metal above to feed down into the holes that are forming underneath. So you want that metal in the sleeves to solidify last, which is why they're insulated sleeves, to keep the metal nice and hot.
And we also have an oxide that comes up through it.
We've got a product called Ferrux, which is like a top topping. So we pour that on and that sets fire. It's an exothermic reaction. That keeps the sleeve hot for longer as well.
Keeps the heat in. All right, let's go to the next section.
Righto.
This bit was really interesting to me because I thought you heated the metal up in a molten furnace with some sort of coals or fire or something, right? That's what you see on TV, but this is actually induction.
It is.
And it uses, I'm going to let you take over.
Okay. So we melt with induction, and the way induction works is we've got this power pack here. That power pack powers this furnace. So this is our non-ferrous furnace where we do all of our non-ferrous casting, so your aluminiums, your bronzes and brasses. And the way it works is it's got a copper coil that's around the furnace there, and that power pack generates a really large magnetic field in that copper coil, and that magnetic field generates eddy currents in the metal. And those eddy currents are what cause the metal to heat up and melt it. So it's much more efficient than a resistor-based furnace, which is like a glorified toaster.
I want to talk a little bit about this machine because this is one of the reasons why we prefer to work with you specifically at Hasco and are leading the game with Australian manufacturing on a global level.
So the way we treat our metal, or aluminium in particular, is we degas the metal, and the way we do that is by pumping nitrogen through the metal. And the reason we do that is it removes impurities, it removes oxide films that form as part of the molten metal process, and it also removes hydrogen, which is absorbed from the atmosphere. And the way it works is this machine here has got a head on it, and it goes down into the bath, spins, generates a vortex, which does two jobs. It pulls the cleaning flux in and stirs it in, and then it'll slow down in RPM so that the bath sits nice and flat and the degassing process starts. So the gas that's being pumped through the rotor head is being split up into lots of small bubbles by the shape of the rotor, because there's teeth on the bottom of the rotor. And then those bubbles permeate through the melt. We do it for about 10 minutes, so that 8 litres a minute, and that cleans out the oxide films from the bath. So oxide films form on molten aluminium almost immediately. So when you see aluminium in the molten state, you've got this film on top, which is like a dry ceramic. And if you've got turbulent metal and it folds over on itself, you get a dry side to dry side, and you get a trapped entrained pocket of air in there.
Yep.
And then the head pressure of the metal after you pour it holds that shut. But once it starts to solidify, it's free to open because that head pressure's not there. So you've got to get those films out, and the best way to do it is with nitrogen degassing on a system like this.
You get porosity and cracks.
Exactly. You're basically pouring porosity and cracks into the casting if you don't clean out the oxide films first. And the reason why we like this machine so much is because it's fully automated. So you get the flow rate the same every time, you get the degassing the same every time. It's got a silicon carbide rotor that doesn't deform and change shape over time, so you get consistent quality that way as well. And it just removes the human element. You just hit the go button and let it do its degassing cleaning cycle, and then you know that the metal's ready to go.
I didn't realise it, but the amount of time, how fast it spins, the amount of teeth, the amount of air, everything is crucial.
Everything is
to the
considered.
second.
Yes.
So it makes a difference.
So you've got to have it repeatable, and the best way to do that is with a PLC controlled machine, which is what we do.
Once we've got the metal nice and hot, I see you heat it up again after the nitrogen process has stopped.
Yep, so we degas it. We'll lose a bit of temperature as a result of pumping the cold gas into the metal. So we just give it a quick nip to bring the temperature back up to the pouring temperature, and the pouring temperature varies depending on what we're making.
700-800 degrees, something like that?
In this case, about 720, 730. And once you've got the metal to temperature, you just skim the top, get it in the ladle here, or in the removable crucible in this case, take it round and pour your molds.
So you've seen all the sections of how a cylinder head in this scenario gets cast, but you're about to see the whole process from start to finish of an RB R0 cylinder head getting made. We're going to show you the actual whole process in one go and see how it turned out. Thanks for the head.
It's my pleasure.
We've got a head. It looks great. We've had it shot peened, cleaned a lot of the sand out of it. Yep. It still needs to go to treatment. We still need to pressure test it, QC it. There's a couple more to go, which you guys are going to pour tomorrow, and we'll have a nice batch that we can go and process. So that, from beginning to end, is how we make a cylinder head casting. And in a later video, we're going to show you how we machine it, prep it, and do the rest of it. But while we're here, you might have noticed a big dirty pile of blocks. We've got one here that we've cut up. People ask us all the time, is it different to an OEM one? And no, we just made it exactly the same, because why would we make it any different? Of course we made it different. So let me talk you a little bit through what we've done. Every 10th or so block, especially while we're getting it off the ground, we cut it up, check it out, make sure we've got consistency, we've got a conformity of production, and we like to make sure that everything that comes out of the factory is exactly what we intended it to be. Because we put a lot of smarts into this block, we're watching it all very closely, not just from a manufacturing point of view, but from a passionate point of view, because Chris from Crest, who's done all of the work behind the scenes with Hasco to get it poured, making the molds and getting everything sorted out. We've been working basically for years on the design. There's a lot of IP that we've put into this block that looks very different to the standard one once you cut it all open. So I'm going to show you a little bit about that, but here is a deck. You can see the deck thickness, which is only 5 millimeters on an RB30 for argument's sake. This one is about 20 millimeters. Now we skim a lot off the top of that, but you can see the inherent detail and strength in that whole deck, which is where all of the RBs crack. You also have the crack above the oil gallery here, which is also now reinforced. On that note, I just wanted to expand a little bit on some of those key benefits that we've created on this particular block, starting with the oil drain backs at the back of the cylinder head. They all go through in a standard gasket formation, but we've actually opened up the cavities that go towards the crankcase and below the center line of the crank, which is a huge improvement over the OEM, as all of that happens well and truly above the crank line, and there's a lot of fluctuations with air pressure that keep the oil up there. So we've managed to get it out all the way through the brace, and you can see here underneath there's actually holes through the brace that allow that oil to get out. We all know that the head drain is crucial on an RB to get the oil out of the cylinder head and down into the crankcase. We wanted to incorporate the head drain so you don't have to bolt it onto the back. Sure, we want to sell you a head drain, but you don't actually need it as long as you use our cylinder head with a block. I'm going to show you why. There's big oil galleries here that go through from the front to the back. You want oil circulating through the head because it cools the valve train. Springs, retainers, valves, all that stuff. You want to keep it cool, and the oil dissipates the heat and gets it out of the cylinder head. They all join onto the big oil galleries and drain backs through the head, as much as the gasket will allow, but then they really open up, as I mentioned before, through the crankcase and down below the brace. So all of that is made to work in conjunction with each other for the best possible result. Knowing that the RB has had oil flow issues in the past, we wanted to alleviate them so you simply don't have to think about it anymore. To list some other key changes we've made to the block, we've got Welsh plugs everywhere. You can do your oil drains, if you do want to run a head drain, turbo drains, and we wanted to put them everywhere so you're not limited to having to run pipes all the way down the side of your crankcase. We've made other changes like removing Welsh plugs from the front and the back of the block. You always have to remove a water pump, timing gear, all the covers that go on the front, or for the back one, you have to remove a gearbox. So we wanted to avoid all of that because we could. But the best part about our Welsh plugs, or freeze plugs, is that they're threaded. Very easy to remove, they seal with an O-ring, and as an added bonus, we're gonna let you have any color you want as long as it's purple. What we've also done is the oil gallery restrictor to the head. Obviously we're going to be running a bigger one now because we can move more oil through the head, and our oil pressure systems have become obviously far superior, moving a lot more volume. We can get it out of the head so we can put more in the head to begin with. We've created a special M7 threaded oil gallery restrictor that is now very easily removable. It's got a screwdriver slot in the top which allows you not only to remove it, but if it does want to come loose, it allows oil to escape the top and you're not seizing your cylinder head because of lack of oil. We've also created a RB25 inspired bottom with smaller holes that stop debris getting stuck and stopping flow through the gallery restrictor. It's our own design, it's modified, it's had some years of experience put behind it, and I'd love to be able to offer it to anyone. So you can. We made it M7 so that you can tap your block and stick one of these bad boys in, or two in this case. Moving over to the front of the block, a clever little thing that we've done is you can see the timing belt tensioner post. We've moved that out so that you can have a clear run for that bolt boss, which is the head stud material goes all the way down to the main stud. So we wanted a clear run at that because we don't know how long we're going to run that head stud down. We wanted the freedom to be able to run a really long, dirty, fat head stud, and we can go up to a 9/16 with this bolt, and this can be modified later. So we wanted to put the smarts in early just so we were ready. If you've ever watched our block cleaning video, getting to the main oil gallery is imperative. So we've put in a removable bung front and back to make it really easy to clean out your main oil gallery. I can't stress enough how important it is to clean a new block. Even with a new block, you should be doing that a couple of times. You can never have it too clean, so please go out of your way to clean the crap out of it, and you're still gonna find stuff in your oil filter to demonstrate how much of a crappy job you did, whether it's a new engine, a rebuilt engine, so please take your time and clean fuck out of it, you can't. If you don't know how important it is to have access to your main oil galleries for cleaning, please go and find the video that we did on how to clean an RB block and head and get real familiar with how to do it properly, and then do it 2 or 3 times in a row, but please go and watch the video, it'll really help. If you're making your own block, you want to make sure that you've covered every potential that anyone's ever going to want. So there's 2 main oil galleries in it. There's an oil gallery pickup that goes all the way to the oil pump. Yes, you can get an oil gallery feed into the side of the oil pump, but we decided to put one right here in the middle of that main oil gallery, just in case you wanted to bypass the standard oil pickup. We've also got a feed port here on your high pressure line. You can drill, tap that, stick in a fitting, and you can get main oil gallery pressure from that or feed it into the side of the block. We haven't come across needing that, but it's there just in case. Looking at the bottom of the block, we've made a few changes as well. So the oil gallery drain backs come through the brace. We've got the provision for a 4-stud main already cast into the block. So we can deck the main cap registers, put in extra bolts. There's a little ledge there that goes the whole way over, and you wouldn't notice it unless I was telling you about it. We've got a huge clearance for the conrod to swing around inside the block as well as the brace, so you don't have to do any clearancing when you're trying to swing a big stroked engine. What you may also notice, piston squirters. Personally, I love them and I'd put them in everything. We've got a provision for a second squirter there, which we may or may not use, but if you notice the new G16 Yaris engine, which is an amazing feat of engineering, has got 3 per bore. So we haven't played around with 2 yet, but we've got the provision there, and I'd love to play around with it in the future. At least it's ready for us when we do get there. Now that you're all caught up on the block, let's head back to the foundry and wrap things up there. Now, let's have a look at the bores. The bores in a factory block, somewhere between 2.5 millimeters and 3 millimeters as a worst case scenario. You can see the thickness of this is a consistent, after machining, 8 to 9 millimeters. So we have completely nailed it when it comes to manufacturing to get a consistent bore the whole way around, including joining onto a very thick deck, and the bores are consistent the whole way down to the bottom. We also have a lot of smarts in where the bolt bosses go through from the top of the deck all the way into the bottom of the mains. In the RB26, it shies away about 2 inches down the bore. It's basically missing after that. We've given it a whole heap of strength when it comes to pulling on head studs. The deck isn't going to move at all. Obviously, it's very consistent, very thick, so we shouldn't have cylinder heads lifting as much because you can put more clamp load on the bolts, and that's a specific that we're going to get into later. They should be able to take a lot more cylinder pressure. The bores are very thick, consistent. They're not going to balloon. You're not going to have any of those issues. But what's really important about this block, other than all the options that we'll get into down the track, is we have not made it out of grey cast iron. We believe this is probably one of the first blocks that's been made out of a ductile iron, which is something that we started experimenting with years ago with our integrated main cap brace. And instead of using a grey cast, which in comparison is extremely easy to cast, we went for the harder option of a ductile cast iron, which for a block application has made it incredibly strong. Twice the strength, for argument's sake, just to give you a number. It's also got some copper mix, which helps with lubrication of piston rings, and we've got a whole heap of smarts within the metallurgy of this material for many certain reasons. It's the best block on the market. We made it to handle in excess of 2,000 horsepower. There will be options with 4-bolt mains It has an option with a standard sort of overlay main brace and our integrated one, dual and 4 bolt options. We're going to get into head gaskets, we're going to get into sealing, and we're still in the process of rolling all of these blocks out now in full production. We're waiting for people to go and make serious numbers. So speaking of ductile cast iron, other than why we're using it, we're going to get Adam here to explain how it's cast, why it's different, why it's more difficult, and the benefits that you can give us.
Sure, so ductile iron as opposed to grey iron, the way that the carbon exists in the metal is different. So in a grey iron, the carbon exists in a flake graphite pattern, and that's why it's so brittle, because the flakes are not ductile. The way we make it is we use a treatment that converts the flakes into spheroids. It's called spherical graphite iron or ductile iron, and that makes the part more ductile. So we're shooting for around a 7% elongation ductility, whereas with grey flake cast iron, you get almost no ductility at all. So it's really going to minimise the chance of there being any cracking whatsoever. The tensile strength's also about twice what you would expect with grey iron. Good for when you're bolting down into the studs. You've got a lot more tensile strength in the stud thread. It's certainly more challenging to cast. It contracts at a greater rate than grey iron does, so it's a less forgiving process. So that's a lot of the work we're doing now, is to engineer out where those problems are likely to be. So we do have access to simulations which we can run. So we will simulate various different conditions, various ways to gate the casting, to get metal into the casting, cooling rates, how to feed it. We can look at temperatures, we can look at porosity indicators, we can look at the flow rate through the gates. There's so many things that we can look at from the simulation that help us design the way that we get the metal into the casting, which is very important for something as complex as this.
To be honest, I had no idea how critical all of those little things are.
Yep.
In manufacturing, obviously machining, there is that level of technicality, and it's very fine. And people don't realise it, and when you show them, they're like, well, that makes sense. And here I just feel like I knew nothing. The minute that I started looking around and asking questions, I realised how much I didn't know. So all of those...
Yeah. Casting something this complicated is certainly an art, and you need to look at all of those factors to get it right.
And you've shown us the simple casting, and in comparison, now I get it.
Overall, it'll be a much better casting in ductile.
And with our extremely thick bore and our at least twice material quality increase...
People are going to have fun trying to break it.
I don't think anyone's going to break it.
I don't think so either.
So we don't really have a limit. Is it going to take 2,000, 3,000 horsepower? I don't know, but we're going to give it a go. But we have done everything that we can as a team to make the best possible block. And this is definitely not just about making money, because we could have made it a lot cheaper, a lot quicker, a lot earlier. This is about challenging ourselves. And I know you mentioned before that I said, is that the most difficult head that you've ever cast? And you actually said it's the most difficult part you've ever cast.
It is. There's a lot going on in there, but it's all there for a reason.
And what's the second most difficult part?
Yeah, that block.
The block.
Yep.
So it's a passion project. We believe we've knocked it out of the park. We've just been cautious and hesitant to just let the floodgates go, because we don't want a single blemish on our record. We are bringing Australian manufacturing back to life. We're proving a point to the world, and it's bigger than just us. We feel that we are patriotically doing the right thing for our fellow citizen, our country that we love. I'm really proud of how far we've come and what we've managed to pull off here and what we are achieving together. And this is just the beginning. So we're proving a point. We're putting Australia on the map, if it wasn't already, and proving why we are the best at what we do. So I appreciate being a partner with you.
No worries. Thank you.
Many years of helping the Australian economy for years to come.
Absolutely. Let's get into it.
Thank you, mate.
Cheers.